Okay folks, so we were going to do an example, so let's do our example. As an example, what I'm going to do is I'm going to look at the function let f of xy be equal to 1 over x squared plus y squared minus 1. Okay, and we want to find local extrema and saddle points if any. Okay, points if any. Okay, so the first order of business is determining the domain of this. So we know for the domain, the only bad values is when the bottom is 0, when the denominator is 0. So we can't have x squared plus y squared minus 1 equaling 0. That can't happen, which of course immediately says x squared plus y squared cannot be equal to 1. Okay, so basically our domain is the whole plane r squared, okay, plane, except the unit circle. Okay, so that's going to be out of bounds. Now let's talk about our derivatives. When are the derivatives 0 and when do they not exist? So if I look at f sub x, maybe it's going to be more helpful if we write this as x squared plus y squared minus 1, the whole thing to the negative 1. Okay, so negative 1 is going to come in front. We're going to have x squared plus y squared minus 1 to the negative 2 times the derivative of the inside. We have this, so this is going to be 2x over 2x, minus 2x, my bad, minus 2x over x squared plus y squared minus 1, the whole thing squared. Okay, so similarly f sub y you can calculate the same way. It's just going to be a minus 2y. It's symmetric, so you don't have to do those calculations again. Thank goodness. X squared plus y squared minus 1 squared. Okay, so that's that. We found the second derivative, so the first derivative. So when is f of x equal to f sub x equals 0 implies what? Immediately that x is equal to 0, right? And f sub y equals 0 implies immediately when that's going to happen when the numerator is 0. So that's going to happen when y is equal to 0. Okay, so these are our candidates for critical points. Of course, it could be a critical point when f sub x and f sub y don't exist. Well, when do they not exist? F sub x, f y, so d and e does not exist. They do not exist. Okay, when we're on the unit circle, of course, when the bottom is 0. Well, this was not in our domain, right? The unit circle, these points were not in our domain, so don't need to consider that. So we have only one critical point. And what is that? That's just the point 0, 0. So we have to apply the second derivative to just this critical point, okay? Nothing else. We just have to do it for this critical point and nothing else. So we need to calculate the 3 second derivatives, fxx, fyy, and fxy. Okay, so let's do this. Fxx. Okay, so what is f sub xx? The second derivative with respect to x. Well, I have to take the derivative of this guy, right? Now I'm going to have to use the quotient rule. The derivative of the top is just minus 2 times the bottom, x squared plus y squared minus 1, the whole thing squared. Okay, minus derivative of the bottom, that's just going to, 2 is going to come in front. You have x squared plus y squared minus 1 times derivative of the inside with respect to x, that's 2x, times the top, don't forget the top, you have minus 2x, and we square the bottom, x squared plus y squared minus 1 to the 4th. Oh boy, okay. Of course, have no fear, this is going to cancel out, right? Everything has an x squared plus y squared minus 1 in it, so we can cancel that out. So this is also equal to, so if I get rid of 1 power of that, it's going to make the equation nicer. this would be just this. Instead of 2, I would have 1. This is just going to go away. And I'm going to have minus, so it's going to be plus 4x plus 8x squared. Okay? All over, what do we have? We have x squared plus y squared minus 1. And we got rid of one of the powers, so it's just cubed. Okay? So, yeah, so that's that. But I'm thinking, did I make a mistake? Hold on. Okay, so let's move on. I checked my work quickly. I don't have a mistake. And I'm not going to simplify this because we just need f sub x, we just need the value at the critical point 0, 0. Okay, so when I plug in the 0, 0, when I plug in the critical point 0, 0, what am I going to get? I'm going to get a minus 1 here. This is going to be 0. Multiplied by that, I'm going to get a plus 2. On the bottom, I'm going to get minus 1 cubed, which is minus 1. So 2 over minus 1, this is minus 2. Okay, so you can do it at home yourselves. Okay. Similarly, fyy is just going to be exactly the same thing, but it's going to be symmetric. Okay, so we're going to have again minus 2 x squared plus y squared minus 1, but this time it's going to be plus 8y squared over this term is going to be the same because it's symmetric, right? Everything is the same. Cubed. Okay, so if we evaluate this again at 0, 0, again we're going to get the same answer. They're heading the same direction, it looks like, so that's good news for us. Okay, so now let's try to find, let's go on to the next page and let's try to find, I'm going to keep it like this. Let's try to find the partial fxy. Okay, so I'm going to take the y derivative of the x derivative. So fxy, if you really have time, you can do the same thing with taking the x derivative of the y derivative. Make sure they come out the same. That way you're doubly sure that you didn't have make a mistake. But I don't have, no, we don't have enough time. So what we're going to do is, we're taking the y derivative of this. Sorry, you're not seeing that. You're not seeing what we're taking the y derivative of. Okay, so we're taking the y derivative of x. Okay, fx. So we're taking the y derivative of this. The top is a constant. We don't mess with it. It's going to stay the same. Okay. Now from the bottom, this is to the minus 2. So minus 2 is going to come in front, right? And I'm going to have this guy to the minus 3, okay, times the derivative of the inside with respect to y. That's just going to be 2y, okay. So we have 8. So we have 8xy over x squared plus y squared minus 1, the whole thing cubed, okay. So now let's evaluate this at our point also. And when we evaluate it, we get at 0, 0. Well, guess what? This is just going to be 0. Okay? So now we can plug in everything into our fxx times fyy minus fxy squared. Okay? Of course, this is all evaluated at 0, 0. Okay, we're all evaluating this whole thing at 0, 0. And we get, what was this? It was, sorry, we found it's on the other page. They were both minus, okay? Minus 2 times minus 2, okay? Minus 2 times minus 2 minus 0 squared. Well, guess what? That's 4. That's greater than 0. So everything's heading the same direction. So this is going to be a local maxima or local minima. And both, they were both the same. fxx was less than 0, right? So it's concave down, which means 0, 0 is a local max. Okay, f0, 0 is local max. So what's the point? F of 0, 0, what's the point? Let's plug it into the equation. What was the equation? Sorry, it's been a long time. It was plug in 0, 0, you get just minus 1, right? Okay, so that's a local, so 0, 0, minus 1 is a local max. Okay, that's how you would do the problem. Okay. We'll do another one in a few minutes. Alright folks, we're back with another example. So we have a function f of xy. It's equal to x squared plus x to the fourth plus y to the fourth plus 4xy, and we would like to find and classify all the critical points. Okay, so the first order of business, this one is a little bit more complicated. Okay, the first order of business is we need to find the points where the derivatives are 0. First of all, the domain of this function is all points in the plane. Okay, so its domain is everything. Domain is all xy, all points in the plane. Okay, so we're not restricted here anyhow. So the derivatives are always going to exist. Hopefully, it looks they're always going to exist. So let's calculate without any further talking. I guess let's talk about derivative. F sub x is going to be equal to, that's going to be 4x cubed. This term is going to be 0, and from here, well, it's going to be just plus 4y, right? And similarly, I can calculate f sub y. That's going to be 4y cubed. This time derivative of y is 1, so this is just going to be plus 4x. And of course, this derivative is 0. Okay? So now, let's work this out. F sub x equals 0 implies, of course, 4x cubed plus 4y. Well, that's equal to 0, isn't it? Well, let's get rid of the force. We have x cubed plus y is going to be equal to 0. X cubed, sorry. So we have what we have. We have y is equal to minus x cubed. Okay. So this is actually a two-dimensional curve. Okay. We got a two-dimensional curve from f sub x. Okay. So it's infinitely many points. Hopefully, f sub y is going to narrow this down for us, which it will. Okay, hopefully it will narrow it down. So similarly, f sub y equals 0. It's going to imply, let's skip the step of dividing everything by 4. Y cubed plus x is going to be equal to 0 this time. So here, if I set it up, this time we're going to have minus x is equal to y cubed, right? Or x is equal to, minus x is equal to y cubed. Okay, so now we can now plug this. Let's take this, okay? Let's take this and plug it into this equation. Why don't we do that? Let's take this and plug it into this equation. Well, from here, actually, let's get x is equal to minus y cubed, right? So if we plug it into this equation now, we had x cubed plus y was equal to 0. But for y, instead of x cubed, I can write minus y cubed. The whole thing cubed plus y is going to be equal to 0. So I have y to the 9, it's minus y to the 9 plus y is equal to 0. So let's factor out the minus y. Okay, so we get minus y times y to the 8th plus, y to the 8th minus 1 is equal to 0. Okay, so there is going to be two solutions, obviously. Y is going to be either 0 or y is going to be 1, right? Y equals 0. So y equals 0 or y equals 1. So when y is equal to 0 from this equation here, okay, then we're going to get x is equal to 0. When y is equal to 1, we're going to get x is equal to minus 1. Okay? So we have two crit points. What are those? 0, 0 and minus 1, 1. The x first, y second. Okay? Alright, so now let's find f sub x. They're not that bad. These ones are easy. There's 2 points this time, but they're easy. What was f sub x? It was maybe, I'm trying to fit it all here. Okay, so it barely fits. 4x cubed plus 4y. I take the derivative of that with respect to x. This guy is going to be gone. So we're just going to have 12x squared, right? And f sub y F sub yy, similarly, it's just going to be 12y squared. Okay. What about f sub xy? Well, that's the y derivative of this, then this term is going to be 0. This is just going to be 4. It's constant. Okay. So now let's evaluate these points at 0, 0. So at 0, 0, what are we going to get? So at 0, 0, well, we'll have f sub x, x, f sub y, minus f sub xy, the whole thing squared. Well, what's that? Everything is 0 here. 0 times 0. Minus now, it's going to be 4 squared, which is 16. Guys, this is less than 0, okay? So what does this mean? 0, 0 is a saddle point. Sorry, you didn't see any of that. My bad. Sorry. Is a saddle point. Okay, so that's going to be a saddle point. So the whole point is, if we plug it into the equation, the whole point is 0, 0, 0, 0, 0, and the z coordinate is 0. It's a saddle point. Okay, what's next? Let's calculate, let's look at what's happening at minus 1, minus 1. At minus 1, 1, if xx, f y times f xy, okay? So I'm just going to call this the delta of it. From the discriminant, I'll use the delta minus 1. So this is a short way of writing it down. So you can always use this discriminant sign. Write the delta. Delta minus 1. Here, let's look at it. Let's plug in minus 1. We're going to get 12. Let's plug in plus 1. We're going to get 12. We get 144 minus, well, it's always, this is 16. This is right, this is greater than 0, certainly. Okay, it's what? It's 128, so it's greater than 0. And let's look at fx6. I can look at fyy also. Evaluate it at minus 1, 1. Well, that was equal to 12, right? So it's concave up. It's concave up. So this is going to be a minimum now. So minus 1, 1. And what's the z coordinate? Minus 1, 1, so that's going to be 1 plus 1, that's going to be 2, plus minus 1 times 1, that's going to be minus 1, 4, so it's going to be minus 2. This is a local, what was it? It's greater than, so it's greater than 0, it's a local min. It's opening outwards. It's concave up. Local min. Sorry. Again, you didn't see any of that. Okay, so it's local min because it's great. It's concave up. It's like this, concave up. Okay, so that was another example. Let me keep this up while we set up. While I set up your next example. And next example is going to be a little different. I thought we would do a closed. Yeah, this one is going to be a little harder. So maybe I'll cut this video off here, and I'll do a separate video for the next example because we're going to do it on a closed region. Take care. Bye bye.